deprecated API? No. No. I want to talk with you about CloudWatch and its Container Insights feature. One metric is called API server underscore requested deprecated APIs. This is the number of requests to deprecated APIs on the Kubernetes server, Kubernetes API server. So can you explain some background on this? What is it? Why might it matter if this metric gives a high reading or has a high value? Or if the data points for this metric, good, because a metric is a set of data points, have a high value. Metrics don't have values, data points have values. The metric API server requested deprecated APIs tracks how many requests are made to deprecated Kubernetes APIs via the Kubernetes API server. To understand why this metric matters, let's break down a few key concepts. So number one, the Kubernetes API server. The Kubernetes API server acts as the central control plane for the Kubernetes cluster. It manages and processes requests from users and internal components like controllers and schedulers to interact with resources in the cluster. When you or any component communicates with Kubernetes, you're interacting with the API server. Deprecated APIs. Kubernetes evolves over time, with new versions introducing improvements and sometimes replacing older features with better alternatives. When certain APIs become outdated, they are marked as deprecated, meaning they will eventually be removed in a future release. However, before their complete removal, these APIs are often still available but marked as deprecated to encourage users to switch to the newer alternatives. For example, if Kubernetes plans to remove an API in version 1.25, it may already mark it as deprecated in version 1.22, giving developers time to migrate their workloads to the newer API versions. 3. The importance of the API server requested deprecated APIs metric. This metric measures the number of requests hitting the Kubernetes API server that use deprecated API versions. Here's why a high value for this metric would really matter. If your applications or infrastructure components are making many requests to deprecated APIs, it indicates that parts of your system are still relying on outdated, potentially unsupported features. Over time, Kubernetes may remove these APIs, which could break your applications if you haven't migrated to supported alternatives. Deprecated APIs are often removed in future Kubernetes versions. If you're not paying attention to this metric, your cluster might encounter issues after upgrading to newer versions of Kubernetes, where those deprecated APIs are no longer available. This can lead to operational disruptions, as your workloads might suddenly stop functioning as expected. Security concerns. Deprecated APIs may no longer receive security patches or updates. This can pose a risk if vulnerabilities are discovered in those old APIs. Continuing to use deprecated APIs can thus expose your system to potential security threats. Performance and maintenance overheads. Relying on deprecated features can complicate maintenance efforts and increase the workload on your team. As Kubernetes evolves, there's a greater risk of bugs or performance degradation with deprecated components, which could affect the stability of your clusters. What to do if this metric is high? Audit your code and configurations. Identify which components or applications are making requests to deprecated APIs. This could involve auditing your Kubernetes manifests, Helm charts, or any custom controllers. Update to supported APIs. Once you've identified the deprecated APIs in use, update your configurations and applications to use the current supported API versions. Kubernetes release notes and documentation will often highlight changes to APIs across versions. And monitor during updates. Pay special attention to this metric when planning Kubernetes version upgrades. If you're making a major version jump, as opposed to a minor version, there's a higher likelihood that deprecated APIs have been removed in the newer version. In summary, API server requested deprecated APIs is a critical metric for ensuring that your Kubernetes cluster is future-proof and stable. A high value should prompt investigation, as it signals reliance on APIs that may be removed in the future. So we have one column for the metric name, one column for the dimensions with any version of Container Insights, and then there are some additional dimensions which you might get if you're using Container Insights with enhanced observability for EKS. And we say that this metric, deprecated APIs, is only with enhanced observability for EKS. The next metric is API server request total 5xx. This is the number of requests to the Kubernetes API server which were responded to with a 5xx HTTP response code. The next metric is API server storage list duration seconds. This is the response latency of listing objects from etcd. This metric is experimental and may change in future releases. Okay, so pretty simple. How long does it take for listing objects from etcd? API server storage list duration in seconds. What would that indicate? Would it be a problem with the network, or would it be that would it mean you've got too many objects in etcd and they take a long time to list? I'm not sure. Next is API server current in queue requests. This is the number of queued requests queued by the Kubernetes API server. This metric is experimental and may change in future releases of Kubernetes. So you can look at the current in-queue requests and use the dimension of the cluster name, or this dimension set, which is a specific cluster name and a request kind. The next metric, the final metric, is API server Flowcontrol _rejected _requests _total. This is the number of requests rejected by API priority and fairness subsystem. This metric is experimental and may change in future releases of Kubernetes. Well, I think we have to investigate that a little bit. So one metric for EKS, only available with Container Insights with enhanced observability, is called It's called API server underscore Flowcontrol underscore rejected requests underscore total. This is described as if it's true that I'm making ChatGPT so knowledgeable as the number of requests rejected by API, and it's capital P priority and fairness, capital F fairness, priority and fairness subsystem. This metric is experimental and may change. Oh, we don't need that bit. Can you provide some information about what this metric is all about? So it's called Flowcontrol rejected requests total. Is it just the number of rejected requests? So the API priority and fairness system is sometimes called APF, priority and fairness. This subsystem is part of Kubernetes' internal mechanism for managing API server request loads, especially in clusters with a high volume of API requests. In Kubernetes, the API server is responsible for handling all incoming requests. As clusters grow, particularly in managed Kubernetes services like Amazon Elastic Kubernetes Service, the API server can experience significant load, especially during peak times or under heavy operational conditions. To ensure that critical system operations are not impacted by non-critical user requests, Kubernetes introduced API priority and fairness in Kubernetes 1.18 as a mechanism, better than Shrek 2, as a mechanism to fairly manage API traffic. So how does it work? Kubernetes APF categorizes API requests into different priority levels. For instance, requests made by Kubernetes system components like Kube Controller Manager are typically given higher priority than user-initiated requests. This ensures that critical system functions are not starved of resources. And then we have this idea of fairness. So that's priority, but we know that when I say fairness, it's a different idea from fairness is about letting all resources have a go. That's really interesting. I know it's different from justice. It's not the same as it's not the same necessarily as equity. Fair. Well, yeah, the dictionary does just say just, unbiased, equitable, legitimate, without finesse, above board, fair trade, the principle that reciprocity should be the condition of free trade. All's fair in love and war. Fair meaning not bad, pretty good, favourable, promising. So among requests of the same priority level, Kubernetes does attempt to distribute the server's capacity in a certain way fairly. Okay, the way it distributes the server's capacity is it does it fairly. This prevents one user or one process from monopolizing the API server's bandwidth. Flow control. The APF system acts like a flow control mechanism. If the API server is under load, APF limits the number of requests processed from the lower priority groups and ensures that requests from higher priority categories are handled first. If a certain threshold of requests is exceeded for a particular category, the system can begin rejecting those excess requests. What is API server flow control rejected requests total as a metric? This metric measures the number of rejected API requests due to APF's flow control mechanism. Essentially, it tells you how many times the API server had to deny requests because the system had reached its defined capacity for handling them under the APF subsystem. Why might this metric be important? One, API overload. A high value for this metric indicates that the API server is under heavy load and is rejecting requests to maintain performance for more critical operations. This could suggest that there is too much API traffic or an inefficient distribution of requests across priority levels. 2. Imbalanced workloads. If your cluster frequently sees a high number of rejected requests in this metric, it might suggest an imbalance in how API requests are being prioritized. For example, too many low priority requests could be crowding out more essential ones, even though they're being rejected. User experience and application impact. If user-generated or application-initiated requests are being rejected, it could result in failed operations, delays, or reduced responsiveness for end users interacting with the cluster. It could lead to frustration or functional issues if the rejected requests involve tasks that are important but have been categorized as lower priority. 4. Performance tuning. Monitoring this metric helps operators fine-tune the cluster's APF configurations. If you are seeing too many rejections, you may need to adjust how priorities and fairness are assigned to different request flows in your Kubernetes cluster. This could involve adjusting API request policies to ensure more fair usage, or redistributing the load. What to do if this metric is high? Review APF configuration. Kubernetes allows customization of the API priority and fairness subsystem. You can create or modify configuration objects such as flow schema and priority level configuration to better control how different request flows are handled. Tuning these can help reduce rejected requests while maintaining fairness across different user groups or system components. Scale your API server. If your cluster is consistently rejecting a significant number of requests, it may be a sign that the API server is under-provisioned. Consider scaling your control plane or increasing resources to the API server to handle more requests efficiently. The third thing we can do, so first thing, review the APF configuration, right? You can customize the APF subsystem. There's these objects, it's called flow schema and priority level configuration. Scale the actual server. Thirdly, reduce unnecessary API traffic. audit the components and the actual applications which are generating the requests. So we're not tinkering now with the API server itself, we're saying, do we need to really be asking so much of it? Some requests might be redundant or too frequent. Reducing unnecessary traffic can relieve pressure on the API server and prevent rejections. And number 4, monitor for bottlenecks. Use other metrics in conjunction, such as the API server latency or CPU usage, to identify potential bottlenecks in the API server. This can help correlate high rejection rates with other resource limitations. So a good exercise would be, well, I'll ask, can you think of any metrics that might be useful? We've looked at the metrics now, we're pretty much at the end of the list. Can you think of any metrics that might be useful for identifying potential bottlenecks in the API server? Conclusion. So the API server Flowcontrol rejected requests total metric gives you insight into how often the Kubernetes API server is rejecting requests due to its flow control mechanism. Monitoring this metric is important for maintaining cluster health, ensuring fair access to API server resources, and minimizing the impact of overloaded API servers on both system components and user-initiated processes. High values in this metric warrant a closer look at your cluster's request patterns and priority configurations. Whoopsie daisy. Okay, back to the docs. NVIDIA GPU metrics. Beginning with version 1.3.0 of the CloudWatch agents, Container Insights with enhanced observability for Amazon EKS collects NVIDIA GPU metrics from EKS workloads by default. The CloudWatch agent must be installed using the CloudWatch Observability EKS add-on version 1.30-EKS build.1 or a later version. For more information, see Install the CloudWatch agent with the Amazon CloudWatch Observability EKS add-on or the Helm chart. These NVIDIA GPU metrics that are collected are listed in the table in this section. Hooray! I do love a table. Let's just provide some context here. So, the documentation tells us that we can look at NVIDIA GPU metrics. What is NVIDIA? I know you think you know, it's a processor, is it? Is that it? But NVIDIA it's a leading technology company that specializes in designing not just processing units, graphics processing units. GPUs, that's its domain, which are widely used in a variety of applications, such as gaming, professional graphics, data centers, they use GPUs, and artificial intelligence. It was founded in 1993. Was that before you were born? After? NVIDIA has become synonymous with high-performance computing, particularly in the fields of visual computing and AI. I know it's called a graphical processing unit, but you should note that that doesn't necessarily mean that it's suited only for visual graphics. It's graphical in the sense that it's a graph. It's a graph, you know, a mathematical entity with edges connecting nodes, so that it thinks sort of in shapes. It's but as it happens, it is pretty good for visual graphics as well. But what is a GPU? A graphics processing unit It's a specialized electronic circuit designed to accelerate the processing of images and video. Unlike traditional central processing units, which are optimized for general purpose computing tasks, GPUs excel at handling highly parallel tasks, such as rendering thousands of pixels at once, which is why they are commonly used in video games, 3D rendering, and graphical simulations. I still don't know. Is it arbitrary that the fact that they are good for video games, 3D rendering, and graphical simulations, is that related to the fact that it is itself graphical? They say, however, GPUs have also found widespread use in fields beyond graphics, including scientific computing, machine learning, and data processing, due to their ability to handle large amounts of data simultaneously, and this is called parallel processing. Parallel is not the same as concurrency. Concurrency is a bit of a con. It's like somebody who says they're pushing two pushchairs at the same time, but really they just move one pushchair forward 5 meters, then they hop over and move the other one 5 meters, and they go between them. That's concurrency. It's a bit of a con. But with parallelism, we're truly doing two things at the same time, at any given point in time. NVIDIA's role. NVIDIA is known for its GeForce GPUs, which are primarily used in consumer products like gaming, PCs, and its Quadro and Tesla GPUs, which are designed for professional and data center use cases. In addition to hardware, NVIDIA has developed powerful software ecosystems like CUDA, Compute Unified Device Architecture. Compute Unified Device Architecture. A parallel computing platform that allows developers to use NVIDIA GPUs for non-graphics tasks, such as deep learning, scientific simulations, and big data analysis. NVIDIA's A100 and V100 GPUs, for instance, are commonly used in cloud services like AWS for tasks involving AI, ML, and high-performance computing. Why do NVIDIA GPUs matter in cloud computing? Firstly, machine learning and AI. NVIDIA GPUs are the backbone of many AI and deep learning workloads. Their ability to process multiple tasks in parallel makes them ideal for training and inference in neural networks, which are computationally intensive. High-performance computing, scientific simulations, financial modelling, and other data-intensive tasks benefit greatly from the parallel processing capabilities of NVIDIA GPUs, accelerating the time it takes to complete these computations. And then a third distinct area is, in fact, visualization. In cloud environments, users can leverage NVIDIA graphical processing units for video rendering, 3D graphics, and even virtual desktops. Cloud providers like AWS and Azure offer GPU-powered instances specifically for these types of workloads. NVIDIA GPUs in AWS and CloudWatch metrics. In the context of AWS and CloudWatch, NVIDIA GPUs are often used in EC2 instances which are designed for GPU-accelerated tasks. AWS provides EC2 instances such as P3, G4, and G5, which come equipped, and they're in the accelerated computing family, which come equipped with NVIDIA GPUs to support machine learning training, video rendering, and similar tasks. NVIDIA GPU metrics are available in CloudWatch and can help you monitor the performance and utilization of the GPUs in your EC2 instances. And we're told these metrics include, but I think we will allow the documentation to tell us about that. So, NVIDIA GPU metrics. And this is only with a particular version of the CloudWatch agent, version 1.30034.0. They say container insights and with enhanced observability for EKS does collect NVIDIA GPU metrics by default, provided you're using container insights with enhanced observability. The CloudWatch agent must be installed using what's called an add-on. Let's try and get that right. It's not an extension, a plugin, a package, an add-on. So EKS add-ons. And you need to use the appropriate version of the add-on. So it's the CloudWatch Observability add-on. For more information, see Install the CloudWatch agent with the CloudWatch Observability EKS add-on or the Helm chart. Let's get some information about that. The CloudWatch agent must be installed to use these NVIDIA GPU metrics. We are told for more information, see install the CloudWatch agent with the Amazon CloudWatch Observability EKS add-on or the Helm chart. What is a Helm chart? Yes, I did mean to say Helm. H-E-L-M. A Helm chart is a package manager for Kubernetes applications. Helm is a package manager. Helm makes it easier to define, install, and upgrade complex Kubernetes applications by bundling them. So bundling the applications into things called charts. What is Helm? It's an open source tool. Helm is an open source tool that helps manage Kubernetes applications using templates. It allows you to define, package, and deploy applications in a consistent and repeatable way. Helm is to Kubernetes what a package manager is to an operating system. Think of APT for Linux or Brew for macOS. It simplifies the management of Kubernetes resources by allowing users to bundle these resources into Helm charts. What is a Helm chart? A Helm chart is a collection of files that describe a set of Kubernetes resources. These resources could include deployments, services, ingress controllers, and more, required to run a specific application. Helm charts are packaged in a way that allows easy installation, management, and versioning of applications with Kubernetes clusters. The structure of a Helm chart. A Helm chart consists of several important components. Chart.yaml contains metadata about the chart, such as the name, the version, and description of the application. Values.yaml contains default configuration values for the chart, which can be overridden when installing or upgrading the chart. Templates This is a directory that contains the Kubernetes manifest templates, which are YAML files. Helm uses Go templating. What is that? Go templating to dynamically inject values into these files. For charts, this directory, right? Remember, templates is a directory. This directory allows you to include other Helm charts as dependencies. And optionally, you can put in a readme.md for Markdown. This provides human-readable instructions or information about the chart. So chart.yaml, values.yaml, templates, charts, readme. How does Helm work? When you use Helm to install a chart, Helm makes the templates. Helm takes the templates which are defined in the chart, injects the values, and they possibly from values.yaml, and generates the Kubernetes manifests needed to deploy the application. Helm then interacts with the Kubernetes API server to deploy these resources. So it makes me think of CloudFormation in AWS. Using Helm charts with Amazon EKS and CloudWatch. In the context of Amazon EKS, the Elastic Kubernetes service, Elastic meaning basically Amazonian, and CloudWatch, a Helm chart can be used to deploy and manage the CloudWatch agent or other monitoring tools on your Kubernetes clusters. The CloudWatch agent collects metrics and logs from your nodes, including those related to NVIDIA GPU utilization, and sends them to CloudWatch for monitoring. By using a Helm chart, you can easily deploy the CloudWatch agent across all the nodes in your EKS cluster, without manually configuring each node. For example, the Helm chart will include the configurations necessary to collect NVIDIA GPU metrics. You can customize the chart with your own values.yaml file to adjust settings like the specific metrics you want to collect, or the frequency of data collection. Why use Helm charts? They simplify deployment. Instead of manually configuring and deploying multiple Kubernetes resources, Helm charts package everything you need, including configuration files and templates, into a single reusable bundle. Versioning. Helm allows you to version your charts, making it easy to upgrade, roll back, or manage your application releases. And parameterization. Charts can be parameterized, so you can adjust variables like resource limits, replica counts. What did we say before? A replica was just a container, or was it just a pod? Replica counts and other settings, I think it was a pod. Replica counts and other settings by just overriding the default values in the values.yaml file. So here's an example use case. CloudWatch agent Helm chart. To install the CloudWatch agent on an EKS cluster using Helm, you would follow steps like this. You would add the appropriate Helm repository, e.g. AWS Helm charts. Then you would install the CloudWatch agent Helm chart. So you'd do Helm, then the word install, then CloudWatch agent. Here's a parameter, -- namespace, Amazon CloudWatch, -- values, custom values.yaml. And EKS/CloudWatch agent is the what? Dimension? Namespace? No, that's the namespace. Customize the values.yaml to ensure GPU metrics like GPU utilization and GPU memory utilization are collected. Okay. Okay. So what is a Helm chart? It's a collection of files that describe a set of Kubernetes resources. For Container Insights to collect NVIDIA GPU metrics, you must meet the following prerequisites. You must be using Container Insights for enhanced observability of EKS, with the Amazon CloudWatch Observability EKS add-on version 130-EKS build .1 or later. The NVIDIA device plugin for Kubernetes, that must be installed on the cluster. The device plugin. The NVIDIA Container Toolkit must be installed on the nodes of the cluster. For example, the Amazon EKS optimized accelerated Amazon Machine Images, AMIs, are built with the necessary components. You can opt out of collecting NVIDIA GPU metrics by setting the Accelerated Compute Metrics option in the Begin CloudWatch Agent configuration file to be false. So NVIDIA is really, it's not called NVIDIA, the option, it's just Accelerated Compute. For more information and an example opt-out configuration, have a look at optional additional configuration. So the first metric is container underscore GPU underscore memory total. And this is the total frame buffer size in bytes on the GPU allocated to the container. Okay, what does that mean? So one of the metrics is called container GPU memory total. It is the total frame buffer size in bytes on the GPUs allocated to the container. What is a frame in this context? Why are we talking about a frame buffer size? Can you provide some background here? So it's called container GPU memory total. So in the context of GPUs and computing, a frame generally refers to a single image or set of data being processed by the GPU at any given moment. The frame buffer is a specific region of memory on the GPU used to hold the data required to render a frame, which could include pixel data, color values, depth information, and other graphics related data. In graphical computing, a frame represents a single image that the GPU renders. Frames are typically rendered in rapid succession to create smooth motion in animations, video playback, or interactive applications. For example, in interactive applications such as games, each frame is dynamically generated by the GPU, responding to user input and changes in the environment. So what is a frame buffer? A frame buffer is a block of memory that the GPU uses to store the pixel data for each frame that it renders. This memory contains the information required to output an image to the screen, including color values for each picture element or pixel, depth information which helps determine which objects in a 3D scene should appear in front of others, and texture data and other properties that affect how the final image looks. Once a frame is fully rendered and stored in the frame buffer, which is just a block of memory, the data is sent to a display device like a monitor or screen where it becomes visible to the user. Why does this matter for containers and cloud environments? In a containerized environment, GPUs may be allocated to specific containers to handle GPU-accelerated tasks, such as machine learning, rendering, or video processing. The container GPU memory total metric tracks the total frame buffer size, in bytes for the GPU allocated to a container. And this tells you how much of the GPU's memory is being used to store data related to frames or graphics-related computations. Even if the task isn't related to rendering images, you're just doing machine learning, you're training a machine learning model, the same concept of memory allocation applies because the GPU uses this memory to store data for processing. The frame buffer size in this context represents how much GPU memory is reserved for holding data during GPU operations, whether for graphics or other computations. Fine, that's fine. Okay, so why is that frame buffer size important? Just the fact that GPUs have limited memory, and it's crucial to monitor how much of it's being used by the different containers, and maybe you could compare it. Remember, we have these dimensions, so you might look at this metric in respect of one dimension, one cluster, and compare it to another cluster. And look, you've got container name, which is part of this set of dimensions. So you can say, well, I'm interested in this specific container and how much of the GPU memory it's using compared to this specific and some other particular container. And here you can see we can even compare individual GPU devices, which presumably is that just the processor itself. So we have container GPU memory total, container GPU memory used, the bytes of frame buffer used on the GPU allocated to the container. Again, we have these 4 dimension sets. Cluster name and namespace and a pod name and a container. Cluster name, namespace and a pod name and a container and a full pod name. Cluster name, namespace, pod name, full pod name, container name and GPU device. Why is there a difference between pod name and full pod name? Thank you, that's very helpful. On the metric, we're told that the dimensions we can use are the following dimension sets. So we have cluster name, we have cluster name, namespace, pod name, and container name. 1, 2, 3, 4. We have cluster name. We have cluster name, namespace, pod name, capital N, and then full pod name, and then container name. What is going on with pod name and full pod name? What is the difference? The difference between pod name and full pod name in Kubernetes comes down to the level of detail and the way pods are named and identified within the cluster. Let me break down the key concepts. What is a pod in Kubernetes? A pod is the smallest and simplest unit in Kubernetes. To be honest, that surprised me, because a pod is a group of containers, so how can it be the smallest unit? Anyway, a pod is the smallest and simplest unit in Kubernetes, representing one or more containers that share resources like networking and storage. Every pod has a name that is unique within a specific name space. pod name? Well, this is typically the base name of the pod, which is either assigned manually when creating the pod or generated by Kubernetes based on certain conventions. If the pod is part of what's called a replica set or a deployment, Kubernetes might append additional identifiers to the pod name to ensure uniqueness. For example, in a deployment or replica set, the pod name might be automatically suffixed, so they add something on the end, with a random or unique string to differentiate it from other replicas. Full pod name. Well, full pod name, this includes the entire fully qualified name of the pod, which may include additional suffixes or strings added by Kubernetes for uniqueness and version control. When Kubernetes creates pods as part of a replica set or a deployment, it does append a unique hash or suffix to the base pod name. The full pod name includes this additional information, which helps ensure the pod name is globally unique across the cluster. So here's an example. Suppose you deploy an application using a deployment in Kubernetes, that's a term of art, deployment. You specify a base pod name like web server. Now Kubernetes may spin up multiple replicas of the pod, and it needs to distinguish between each replica. Here's how the names might look. So we'd have web server and web server dash 598D8D6B dash ABC12. So that's the full name. Web server dash, and then a string, and then a dash, and then another string. So in this case, pod name is just the base name, and full pod name includes the full name with the suffix, which Kubernetes automatically adds to ensure uniqueness across the replicas, across the versions of the pod. So pod name is useful perhaps when you need to refer to all the pods that do have that same base name. Full pod name is needed when you want to uniquely identify a specific pod instance, particularly when dealing with deployments or replicas, where multiple pods share the same base name. Why the difference matters in metrics. When monitoring your Kubernetes cluster, different levels of granularity are needed depending on the use case. So we can already think why, because if you have multiple pods, each of them is called a replica, do you want to measure all of them? If you do, maybe you want to use pod name. Let's just read. So if you're interested in aggregating metrics, like the total GPU memory usage across all replicas of a specific pod, you might use pod name, to refer to all the pods with that same base name. But if you want to drill down into the performance or behavior of a specific instance of a pod, for example, one particular replica, then you would need the full pod name to identify and monitor that exact pod. In the dimension sets for metrics, you have the flexibility to choose between pod name and full pod name based on the level of detail you need. If you're interested in metrics for all replicas or all versions of a pod, you can use pod name. If you need to track a specific pod instance, you'll use full pod name. Thank you very much. So we have container GPU memory total, container GPU memory used. So you see this memory total is not memory used. It's not how much memory we have left. What's our memory total now? No. It's how much have we allocated to the container. So it's kind of an ideal, it's in theory, how much is our memory total? That's what it means. If you want to know how much is being used, you have to actually look for this metric, which is container GPU memory used. Third metric, container GPU memory utilization. Oh, well, you think, my word, what is this one? Utilization used? Well, this is the percentage of percentage. So utilization, perhaps, I don't know, make it so that the Z makes you think of the percentage sign. Z, the letter, has a diagonal line in it, like the diagonal line used in the percentage symbol. Container GPU power draw. This is the power usage in watts of the GPUs which have been allocated to the container. Again, these 4 options for the dimension sets. So that's number 4. Number 5, container GPU temperature. Oh my word. And it's not metaphorical. This is the actual temperature in degrees Celsius of the GPU allocated to the container. Can you believe that you can actually detect that? On your computer at home, you can actually get that information about the temperature of a chip in the middle of who knows where, perhaps the Nevada desert if you choose it, straight to your desktop screen. This is CloudWatch. Remarkable. Container GPU utilization. So we're thinking it's a percentage utilization with that Z in it, and if it's the American spelling, which it should be, we're on AWS. And of course now this is, but no, how is that different? Container GPU utilization. Well, what we were looking at before was container GPU memory utilization. So there's container GPU memory utilization, and then just container GPU utilization. So this is just not the memory of the thing, the thing itself, the graphical processing unit. How much of that GPU are we using? Or, yeah, node GPU memory total. The total frame buffer size in bytes on the GPU allocated to the node. So this is this is not how much we're using, it's the total frame buffer size. So it's the memory total. Then we have node GPU memory used, and because it's not the word utilization, it's not a percentage, it's actually just a number of bytes. It's the bytes of the frame buffer being used. So that's node GPU memory used, and then we have a third one, which is node GPU memory utilization. Percentage, the percentage of frame buffer used on the GPU allocated to the node. Now, you may not have seen, but we now just have 3 dimension sets: cluster name instance ID and node name, and cluster name instance ID, instance type, and node name and GPU device. So we've no longer got the any talk of pods in the dimensions. That makes sense because the metric is at the level of the node. So we don't have full pod name. We've got instance ID now, and we didn't have that option for the container, so we had container GPU utilization. Well, you can't do that by instance ID. If you're interested in the container GPU utilization for your dimension, all you can say is, I'm interested in this cluster, this namespace, this pod, this container, but not a particular instance. I mean, we have a separate metric for that. So we have so anyway, we have, I don't know where we've got up to, but pod now. So I think we were on the metrics to do with node. So we had how many to do with node? 5. Right, so container, then 1, 2, 3, 4, 5, 6 metrics to do with node. One on temperature, 1 on power. That leaves 4. Well, 3 are to do with memory, and the final one's to do with just the GPU itself. And then we move on to the node GPU utilization, just how much of the node of the GPU are we using. And then we move on to these pod metrics, groups of containers. even though ChatGPT just called a pod the most fundamental unit. And the pod GPU memory total is the total frame buffer size in bytes on the GPU allocated to the pod. Remember, what is a frame buffer? A frame buffer is just a block of memory. A frame is a particular image that we present at a particular point in time, so hence we have a frame buffer size. So we have pod GPU memory total, pod GPU memory used, and pod GPU memory utilization. We're familiar with that triplet. Pod GPU power draw, pod GPU temperature, and pod GPU utilization. The percentage utilization of the GPUs which have been allocated to the pod. And we're going to finish there just for now.